Hello, Applied Physics students. Here is your teaching video for the Concept Development Practice, page 32.1. This is talking about Coulomb's law. And again, remember we have Coulomb's law here, right? And Coulomb's law just says that the force between electrically charged particles is equal to a constant, okay? Times the charge of particle 1 times the charge of particle 2 divided by the distance between the particles squared. So, question number 1 says, the diagram is of a hydrogen atom. Letter A, label the proton in the nucleus with a positive sign and the orbital electron with a negative sign. So the center of the atom is our nucleus, so here's our positive, and this out here is our electron. So here's our nucleus. And inside the nucleus is where we find that proton, which has the positive charge. The electrical interaction between the nucleus and the orbital electron is a force of, well, we have a positively charged nucleus and a negatively charged electron, right? And we know that like charges repel, right? That's pretty important, that like charges repel, and opposite charges attract. So, since we have a positive and a negative charge, this would be an attraction. So this would be a force of attraction. According to Coulomb's law, okay, and again, remember this is just a constant, and we aren't going to do any math with it, so we don't really need to know the number of the constant. F stands for force. Q is the size of the charge. And so that's there twice because you're talking about the size of two different charges. And D is the distance between the charges. And this is an inverse square law. So remember, things that are in our numerator are going to, or in the top of our fraction, those are going to be directly proportional. So that means as either the size of my charge increases, my force is going to increase. Because distance is in the denominator, as my distance increases, because it's in the denominator, it's going to reduce, okay, or decrease the size of the force. So remember, these are directly proportional. So as one goes up, the other goes up with force. And because this is in the bottom, these are inversely proportional. And so that means as one goes up, the other would go down. So, according to Coulomb's law, if the charge of either the nucleus or the orbital electron are greater, the force between the nucleus and the electron would be, right? So that's directly proportional because we're talking about the charges. So if the charge of either of them is more, the force will be greater. And if the distance between the nucleus and electron were greater, the force would be, again, we're talking about distance, which is in the bottom of this fraction, which means it's inversely proportional. So if one goes up, right, which is what this is saying, okay, if the distance was greater, the force would be less because they're inversely proportional. So now a little bit of math, but this isn't hard math. If the distance between the nucleus and electron were doubled, right? So what we're saying here is everything else stays the same, but I have twice the distance, and I'm going to, okay, square it, right? 2 squared is 4, so I'm going to have what I had over 4 times my distance squared. Now, to figure out what happens, remember I have to pull that 4 out, but it's a 1 over 4. So when I kind of pull that out, it's 1/4 the amount. So if the distance between the nucleus and electron were doubled, the force would be 1/4 as much. Remember in Applied Physics A, you should have looked at something similar to this when you talked about the law of universal gravitation. Number 2, consider the electric force between a pair of charged particles a certain distance apart by Coulomb's law. If the charge on one of the particles is doubled, right? So again, we want to kind of compare this. So we have F equals K Q1 Q2 over D squared, right? That's what we start with. So now what we're doing in this letter A is we're doubling the charge. So we have F equals K 2Q1 Q2 divided by D squared, right? So I just have that 2, so I need to bring that 2 kind of out in front. And I can just bring it straight out in front because it's in the numerator. So it is going to be doubled. The force would be twice as much because we would have 2 times this original force. If instead the charge on both particles is doubled. So now, right, originally, again, we're still this to start with, but now we have F equals K, 2 times Q1, 2 times Q2 divided by D squared, right? So that's K 4 Q1 Q2 over D squared. And again, I want to bring that 4 kind of out in front, and I can do that because it's in the numerator. So if instead the charge on both particles is doubled, the force is quadrupled, right? So that's letter B. C, if instead the distance between the particles is halved. So force equals K Q1 Q2, but I have 1/2 the distance squared, right? So 1/2 squared is 1/4, my distance squared. Now, I want to bring that out, but remember that's in the denominator. So the only way to bring that out is to get rid of that so it's not in the denominator. In the bottom, I have to multiply, okay? I'm going to multiply by its reciprocal, right? So reciprocal just means I flip that. So the reciprocal of 1/4 is 4. So I pull this out and I do that flipping part as well. So that means that I am bringing a 4 out in front of this. So if instead the distance between the particles is halved, the force is quadrupled. It's 4 times as much. If the distance is halved, okay, so again, F equals K, okay, the distance is half, so 1/2 the distance squared, and the charge of both particles is doubled, 2Q1, 2Q2, the force is blank times is great. So, K, we have 4Q1, Q2 divided by 1/4 D squared. Remember again, to get rid of this, we're going to multiply by its reciprocal, so that becomes a 4. So we have 4K. We still haven't dealt with the 4 that's on the top, but that we just bring out. But when we bring it out, that's a 4 times a 4. So that's 16K Q1 Q2 divided by D squared. So the force is 16 times as great. Again, remember, we did this, at least the students that I had in class in Applied Physics A, we looked at this similar problems with the law of universal gravitation. This is an inverse square law, okay? So again, the force is the square of the inverse of the distance squared. So that's a little bit more about Coulomb's law and how it works. Have a great day, and I'll talk to you tomorrow.